So in this video we're going to be looking at the rate of change. So the average rate of change by definition is, well, like in relation to the change of a quantity given by a dependent variable. So for us, let's say it's y. So the delta in y over a corresponding change represented by another independent variable. So let's say x. So for us, mainly what we're going to do in many cases will be a change over time, but we can keep an open mind. So if f of x, if y is equal to f of x, then, and say x1 is smaller than x2, then we can say our rate of change, our delta y over our delta x, is f of x2 minus f of x1, which are y values, over x2 minus x1. And this is going to make more sense in a bit when we look at an example. I'll just leave that there. So let's look at an example with, say, bacteria. Say we have time. So our time in hours, let's say we have 0, 2, 4, 6, 8, 10, and then we have 850, 1122, 14, 81, 1954, 2577, 3400. See, we're looking at this chart. And say we have bacteria here. Now we see at 0 hours we start off with 850, and then we have 1122, and then we have 1481, then 1954, 2577, and 3400. So say we want to look at the rate of change. And we want to see the difference in the rates of changes between each one of these intervals. So let's look at 0 to 2 hours first. So let's do the rate of change between those. How much bacteria did we have grow in the first 2 hours? So the difference in the bacteria is going to be 1122 minus 850, and the difference is going to be 2 hours minus 0 hours, and that'll give us 136. So let's just write that here. So 136 let's put delta just to see the rate of change. Now we can do the rest for the others. So say we have oh wait, that's gonna get confusing. steady rate by 2. So all I need to do is take the difference between this value and that value and divide it by 2. So this one will give me 179.5. 1954 minus 1481 should give me 473 over 2, 236.5. This one, 2577. Subtracting 1954, that should give me 623, and then divide that by 2. I should get, what is it, 311.2, sorry, 0.5. 311.5, and then we have 25, no, sorry, well, 3400 minus 2577. When you subtract those two, you should have 823. You divide that by 2, you should get 411.5. And you can see the rate of change is growing. So not only is the bacteria growing over time, the rate at which it's growing is growing as well. So if you were to draw that out, well, here, and you had like, say this is 0, then you had like, well, let's draw these out. So 1,000, 2,000, 3,000. You start here, and then you do like intervals of 0, 2, 4, 6, 8, 10. It would go somewhat like from here. That's 10. Let's do 2, 4, 6, 8. 6 is like somewhere in 1900s. 8 is like 25 something. It'd go like so. My point is, it's not like it's a straight line, it's actually a slight curve, and that is the rate of change, which is changing. And you can actually find the rate of change at any given point by finding a secant line. So what is a secant line? So say you have this curve. And you want to find out the rate of change here. All you have to do is plant a line that goes through that point. Or sorry, if you want to find the rate of change between, no, this is a tangent line that I just described. Ignore that. That is a rookie mistake on my part. If you have a curve and you want to find the rate of change at between 2 points, say from here and here, you want to find the rate of change, you draw a secant line that goes through both the points, and that will give you that relation. Almost confused a lot of people there. So let's tackle one more example. example of, say, the real world where you have say you're doing a car rental, and the car rental charges you $35 per day, plus an additional 15 cents per kilometer that you drive each day. So we can say that we're smart enough to write a function for this, so the cost of the distance or the daily car or the days, the cost of each days is going to be 0.15 times d being distance in kilometers plus 35 on any given day. So now we can look at the average rate of change here. So if you were to draw this out or sketch this, we could say that this is the distance. Say you start off at 0 and you can do 50, 100, 200, 300, and so on. Oh, that's not even, should be 150 and 200. Then you do the cost, 10, 20, 30, 40, 50, 60, 70, 80, and so on. So we know that if we were to draw this out, start at 35, and then we do 15 cents per kilometer. So the more she drives, it just keeps going. So we can tell this, or we can see right away that the rate of change is constant in this one, in this example. Because our line is straight. And if you were to pick any 2 points here, say 0 to 100, let's say at 100 she's at 50. Let's just say that's true. And then you were to plug it into the formula delta C over delta D. Delta being the change in the cost. Oh, this is the cost here. The cost, the charge at 100. So C at 100 minus C at 0 over the change 100 to 0. So C at 100 would be 50 minus 35 divided by 100. So then you'd have 50 minus 35, which is 15 divided by 100, which is 0.15. And that's exactly what she's getting charged anyways per kilometer. So we can confirm that the rate of change for her rental is only dependent on this, on her kilometers driven. So yes, that is us using math to state the obvious. So yeah, rate of change, heavily used in physics and chemistry. So stay tuned in the foreseeable future when we cover physics it's going to be fun to learn about all the different types of deltas and rates of change. So yeah, that is